Holy moly. Look at this lag. Alright. How do I get the link? Hey folks, everyone's here. Hello. Vic. First off the bat, good work. Buddy, just going to post on Twitter that we are live. And we will get straight into it. Just to send one more link to chat. Or to a chat. We'll get stuck in. All right, so what we're working on this evening, don't know how long it'll take, but shouldn't be too long, is implementing a UNet in PyTorch. So I've done a few of these in my time. You know, a lot of work in the medical imaging space naturally results in quite a lot of UNets, but this is kind of the OG of a lot of segmentation models these days. And tonight we're going to start with this original version straight out of the paper. You know, this paper is wild. It's had like 40, almost 50,000 citations. But yeah, from Olaf Rodenberger, Philip Fischer, and Thomas Brox. So we'll implement this in PyTorch on a bit of a dummy data set, talk through a few things, a few areas where it's worth putting in a little bit of modernization. But then in subsequent streams, what I want to do is start adapting this. So we've got things like ResNet blocks, we've got things like attention, and all, I guess, of the modernizations that have come with the UNet. But my goal here is to sort of go through each of them, talk them through why the improvements were made. Yeah, let's get stuck into it, shall we? So I've done a little bit of boring work already just to save us having to type things like the imports. For reference, I'm using Paperspace here. That gives us the opportunity to run this. I will share this code at the end. I'll throw it up and I'll update the video description with the link to the notebook. So I'll export it from here so you can run this on your own machine. But we're running on, let's have a look here. We're running on one of the GPUs. So I have a paid account on Paperspace. You can get free GPU without a paid account, but a lot of the GPUs were unavailable when I had a look a minute ago. So I got a paid account, run the P5000s. It's got about 16 gig of GPU RAM. Should be more than enough for what we're going to be doing this evening. So what we are going to do is build this UNet. The data set that I've chosen is the Oxford 3 TPET data set. So I'll just start this running and I'll just show you what we got here. It's a pretty basic data set. And I'll talk through what some of this code does in a sec. So let's just do this. Plot.imshow. Dataset 0, 0. So that's going to be the image. So this dataset's a bunch of pets that somebody has hand segmented. Oh, didn't like that. What did I do? Oh, yeah, because they switched the things. The order of them. Let me just quickly ditch this tensor transformation for the sake of showing you. So we got pictures of dogs and cats, and we have some segmentations of those dogs and cats. Oh, sorry, I already did that in the code, so we don't need to do that. And then we've got the segmentation. So in the original dataset, there's actually 3 classes, which is the animal itself, the outline of the animal or any occlusion. So if there's something covering, say, the cat's face, it hides that, and then the background. Now, we'll go back up here and have a look at some of the code that I've already written, which just processes this dataset and gets it into a bit of a usable form. So quickly on the imports, everything you'd expect. We're using PyTorch for this. I did most of my AI work previously in TensorFlow, but decided recently to switch over to PyTorch, give it a go, learn some new things, and it's been pretty fun. I would definitely recommend PyTorch for those getting into machine learning, the API is quite accessible. Anyway, we're importing some stuff from Torch Vision because we're working with images here, and Matplotlib for a bit of visualization, NumPy for a bit of, or NumPy, as I prefer to call it, for a bit of mathematics, and we set a manual seed just so that when you run this on your machine, you should get reproducible results. Now, one of the reasons I picked the Oxford 3-pet database is because it has this download option, which means that if you don't have it on your machine, PyTorch will just grab it, unzip it, and prepare it all. Some of the other ones you need extra libraries and things like that. It's a bit of a boring data set, but that makes it super easy and it's less fuss for you guys. So hopefully that's helpful. So we'll start here. So we're grabbing the data set. We're just throwing it in a folder called pets. We want the train val split. We won't really bother with the test split in this example. We might extend that later. We want the segmentation types as opposed to the object detection types, which is bounding boxes. We want to download it, and then we want to run these transforms. Now, these transforms take the image files and make a bunch of user-defined transforms to get them into a state that we're happy with. And you can see these up here. So we've got transforms on the images themselves, so that's the pictures of the cats and the dogs. And to make this quick, I've resized all of the images and all of the labels to 128 by 128. In the original dataset, they come in all different sizes, but for consistency and speed of training, I've scaled them right down. You can obviously make these bigger if you want to, and go for some more advanced segmentation, but for the educational purposes of this video, 128 should be plenty. Now, the image itself is pretty simple. It's just resize and convert it to a tensor. There's a little bit more going on in the targets, and the reason for that is the original labels in the dataset are floating points, 0, 1, and 2. And the labels don't really make a lot of sense. It's like 1 is the animal, 2 is the background, and 3 is the occlusions or something like that. And we want to get it to be 1 is the animal, 0 is the background. Just looking over at chat for a sec. Does the dataset have pre-annotated annotations? Yeah, it does, which is very handy. Some of them are a little off, especially with that bounding or surrounding area annotation. It makes them a bit funny, but for the purposes of this demo, it's plenty useful. And you can sub your own dataset in here and hopefully extend this to what you need. And then does consistency help with anything other than speed? So we do want them all to be the same size. You can train units to operate on variable size images. It requires a lot of extra configuration that I didn't want to add to the complications of this video. So I've done a few things in this setup and when I did a little bit of experimentation before this stream to try and simplify this as much as possible, because my goal here is that you understand how all of this works at the end of the day. And yeah, hopefully that all makes sense. So these lines here, 8 through to 11 is really just particulars of the Oxford Pet dataset. It converts the labels from floats into integers. It does some tricky mathematics to basically move them into a useful space. It's not really all that interesting how this works. I just did the hackiest thing I could think of to get 1s and 0s, or 0s and 1s as the labels. But know that after this whole setup, we've got 128 by 128 labels where each pixel is the index of the true label. And that'll be important a little bit later on when we look at loss functions. So to get talking about the actual model, this is a picture right out of the paper, which I inverted so we get some nice dark mode, but I also annotated it with these letters because as we build this out, we'll refer back to some of these sections in the model. You can see that the way that this works is we have an input image. In this case, it had 1 channel, but ours have 3, R, G, and B. and it does a number of 3x3 convolutions followed by a ReLU activation, and then it does a max pull 2x2, and then repeats that process all the way down. And then as it starts to come back up with an upconv, and which is a linear interpolation up followed by a convolution, it then does something pretty interesting. And this is the big, I think, insight that came out of the UNet paper, is it concatenates the feature maps from the earlier stage of the model onto the feature maps from this upconv, and then feeds that through another couple of convolution layers. And what it seems to be is that having these copy and crop, as it calls it, we'll talk about crop later, we kind of ditched the cropping bit because it's annoying and finicky, seems to really have been the breakthrough of the UNet. And it gets all the way back up to 64 features here, and then we have a final 1x1 convolution to get us to the number of classes that we need. In our case, that's going to be 2 classes. So some other work I did down here is just define a basic training loop for a generic UNet model that we're yet to write. And we'll get to that when we get to it. But the model that we're going, or the class that we're going to be filling in here today is this one. So I've got the skeleton of it here. We'll build a couple of helper classes along the way. But we want to build a UNet. And we have 2 parameters to our UNet model. It's the number of channels, which in this case is 1, in our case is 3, and the number of classes, which in this case was 2, and in our case is also 2. And you can see when I've instantiated it down here, we've said 3 channels in and 2 channels out. But if you're using this for your own projects and you've got a different number of channels or classes, you should be able to change that pretty easily by the end. All right, so let's start to talk about how I, as a machine learning engineer, but doing this for a while, would start to think about how to break down this problem, and in particular in PyTorch. So what I would do first is notice here that there are a number of very similar looking blocks or groups of operations that you can see here. And these are the ones that I've already pre-labeled, so that might give you a little bit of a hint about what we're going to do. So we seem to have this recurring pattern of 3x3 conv ReLU twice on 1, 2, 3, 4, 5, 6, 7, 8, 9 different blocks. And so what that says to me is, okay, let's abstract that out into its own module and then use it in our code, and that'll keep our code a little bit cleaner. So let's do that right now. So we're going to make a new class, and we're going to call that conv block. And similar to the UNet itself, it's a PyTorch module, which means that we need 2 functions. We need init, which takes the self. It will take more stuff, but we'll come back to that in a second. And we need forward, which takes self, and it takes the actual input vector. So thinking about what the initialization parameters should be here, the main thing, given that they're all 3x3 convs, they're all using ReLUs, we don't really need to make that a parameter. We could if we wanted to, but it doesn't seem necessary here. The big thing that seems to change is the number of parameters at the start and the number at the end. So you got 1 to 64 here, 64 to 128, and so on, both going down and coming up. So we'll say that the 2 parameters here we have is the number of features in, and with our lovely type hints, we will make those both integers. So we've got going out as well. So then what we need to do is define the sequence of steps in the init model. So we'll say we've got to do our super, which initializes the module, makes it talk to PyTorch in a happy way. Don't forget to do that. It will give you an error if you forget, but it's easy to do. So getting straight into it. We want to have a number of convolutions. So we're going to use the sequential function in PyTorch, and what that lets us do is it defines a number of steps as arguments, and then it'll run if you pass x into a sequential, it'll pass it into each one in that loop in turn. And so you can see here we've got a recurring pattern that we're going to define in our sequential. We've got a conv2d. I have some of the docs open on this other screen if you're wondering why I continue to look in that direction. So we've got a convolution 2D. So for the very first one, the in channels is equal to fin. So you can see up here, the very first conv, the in channels is 1, and then the out channels for that one will be whatever f out is. In every case, the kernel size is equal to 3 by 3. The stride is the default. And what we're going to do here is make padding same. So I'll explain what that's for. In a typical convolution, you can imagine sort of a grid and that convolution going over it. If you don't add additional padding, the edge pixels themselves don't have enough data to map that full 3 by 3 convolution. So if you imagine a 6 by 6 grid, let's see if we can draw a little picture here in the comments. So imagine each one of these is a pixel. And for simplicity, we'll talk about a 2 by 2 convolution. That would take these two e's and these two e's. Well, let's do 3 by 3 because it actually is more similar to what we're doing. It would take these 3 e's, these 3 e's, and these 3 e's, and convolve that with the kernel, whatever that happens to be. But that gives us a value for this e here, because it takes the center pixel at the center of the kernel and then takes all of the pixels around it. So the question is, what do you do with these outer rows and outer columns that don't have enough data on the other sides of it to form a full convolution? And your options are to drop them, so to not add any padding, and your output image will be slightly smaller than your input image, or you can add padding. And you can add padding as an integer, in which case it'll add however many boxes of additional size to your image before doing the convolution. You can choose to fill those with zeros, or you can mirror whatever pixels are on the edge. By default, it does zeros. But if you put this parameter in same, PyTorch will work out how much padding to add to ensure that your feature maps have the same size going out versus going in. And you can see here, this starts to get smaller each conv, so it's 284 by 284, then it loses a couple, then it loses a couple, and then they do this sort of crop and they drop it down. Oh, sorry, this one here is actually just halved. They do a crop later on. That is technically the original UNet setup, but I find that it's often an area to make mistakes. All it really does is sometimes you get some artifacts at the very outer edge of your convolution, of your output features, but with enough training data, it tends to go away. And I'm a big proponent of simplicity, especially when trying to learn this stuff. So we're just going to ditch that for today. We don't have to do as many crops, and our overall code is going to be cleaner for these purposes. So the next thing we're going to do is a rel u. And then we want to do, so you can see here we've got 2 convolutions per layer. So we've got another one, conv2d. This time the in channels is equal to f out. So it maps the same size in each case. So you can see here it went from 1 to 64, and then this one went from 64 to 64. So it maintains that size in that second set of convolutions. Is there an image size where you must use padding? No, not necessarily. I mean, padding is, sometimes you want images to be square, or you want them to be powers of 2, so like 64 by 64 or 128 by 128. for like GPU optimization reasons, but it's not strictly necessary. You can get away with it, but what tends to happen in a lot of these papers, and you can kind of see it here, is you'll sort of pick sizes and padding so that when they get divided by 2 a bunch of times, they are still whole numbers. So you can see here 280 becomes 140, 136 becomes 68, 64 becomes 32. Because otherwise what happens is you end up with sort of half pixels that don't really get defined anywhere. And again, it's just a little easier if it makes sense. 128 by 128, mind you, is quite small. But there are many applications where 256 by 256 is not that small, and it's quite common. So medical imaging, for example, depending on what kind of, say, MRI scanner you have, your output image may be in the order of 200 to 300 pixels along one of the dimensions. So while this is a bit of a toy problem and a bit of a intentionally small example, it doesn't mean that it has no real-world applications. And what you find here is you can go pretty large. You often just need to make the batch size smaller. And depending on your GPU, it'll obviously take up more RAM. Let's jump back here and finish this one. 3 by 3. And again, we'll do padding equals same. If you are watching this stream right now, and I can see that a couple of people are, and you haven't subscribed, we are like crazy close to 100 subscribers, and that would make me feel happy if you happen to subscribe. No pressure, obviously. You're welcome to watch these videos and not subscribe. No stress, but thank you for being here. Obviously, Tom, the other half of the channel, asking all these great questions. Hopefully I didn't just spoil Tom's attempts to secretly pose some questions. But that's who Tom is in the chat. All right, so this is our conv block. You'll see they're reused a whole bunch of times, and the forward pass for this one is pretty simple. We just return self.convs x. So what this is going to allow us to do now is to define a bunch of these convs blocks rather than define a bunch of these sequentials. And it means that if we want to tweak things like the feature sizes, we can do that pretty easily. And Vivek, thank you for subscribing. It's good to have you here. Alrighty, let's see. The other thing we want to do, which is a little bit more complicated, the max pools are pretty simple. The other sort of 2-step operation are these upcoms. So we'll make a module for that one as well, because we do that a number of times, and it's just nice to have these modules. Man, this smart indenting is doing my brain. All right, so upconv module def init. But yeah, as I said, I spent most of my time previously in TensorFlow. Still think TensorFlow is a great machine learning library. Picked up PyTorch recently just as a bit of a challenge to myself. If you are in a similar boat and have only worked in TensorFlow or one of the other libraries, definitely recommend giving it a go. I had a weird bias against it for a while because it was originally made by Facebook, which I know sounds real strange, but I don't know. It just seemed odd to me. But I'm glad I got over that, especially now that I'm pretty sure it's managed by, I don't know if it's the Apache Foundation or something more general, but it's a consortium now. It's a very good set of tools. Lots of good libraries for it too. Anyway, so I've read the original paper, but typically at this stage you would also need to read the original paper to work out what an upconv 2 by 2 is. But what it is it's an upscaling of the image. In this case, it's just literally your classic sort of upscale and then interpolate, followed by a 2 by 2 convolution. There are a couple of other ways to do it. There's a transpose convolution where you sort of learn the weights to do that. From some experimentation with some work we did at Maxwell Plus on medical imaging, the bilinear interpolation plus convolution works pretty well. And I don't think the paper itself was really that stringent on this. We've done the testing and we've seen it hasn't made a huge difference. Sort of Tom's question there, which would you recommend studying? Look, if you're a professional working in a company, just use whatever they use. Otherwise, I think PyTorch has a bit more of a sort of Python flavor to it. If you've done a lot of work in NumPy, Pandas, things like that, PyTorch is going to feel pretty familiar. But you really can't go wrong with TensorFlow and Keras these days. That's also pretty approachable. So back to the upconv. We've got two steps here. We've got the actual up itself, for which we're going to use the built-in torch upsample function, in this case with a scale factor of 2. And that basically means take each of the dimensions and double them in size. And the mode that we're going to use is bilinear. You can use nearest neighbor, you can use trilinear and a bunch of other interpolations. They all kind of work the same with enough data. But I found that sometimes if you do nearest neighbor, you can get this sort of repeating checkerboard pattern on some of the later outputs, which is not very nice. So bilinear tends to smooth things out. And really what this means is that, if you take let's say a 10 by 10 image and turn it into 20 by 20, you have to work out what to put in all the missing pixels. In nearest neighbor, it'll just take the value of the pixel next to it, and then you'll get sort of a pixel art style upscaled image. In bilinear, it'll take the 2 pixels on either side and it'll do a linear interpolation. The reason it's bilinear and not just linear is because it does it in the x dimension and the y dimension. And then we've got a conv. Yeah, I agree, Vivek. I think Keras is, I think you're absolutely right. Like it is easy to get stuff going, but when you get into the real work of ML, which is like tweaking models and testing things and iterating through, you often have to like pull big chunks of your code out and then rewrite it into a more verbose form to, tweak something in the middle. Whereas it seems to be a lot easier in PyTorch. One of the things we'll do a little later on, spoiler alert, is put a bit of batch normalization in here. That's one of those things that I found can really help. It wasn't in the original paper, but it's definitely common practice now. And doing that here is super easy. It's probably easy in Keras too, but I think the general point still stands. All right, we got a conv 2D. In this case, we've got, I guess it's still f in, out, equals f out, kernel size equals 2 by 2, in this case, I think. Yeah, 2 by 2. You could probably get away with 3 by 3. I think when I originally did this, I just did 3 by 3. Really what this is trying to do is learn a sort of smoothing interpolation function. I think in the original they probably didn't do bilinear interpolation, so they had this extra conv. You may even be able to drop it, to be honest. But I haven't tried that, and we're going to stick true to the original as much as we can. So again, we want the same size padding. All right, and that's the only 2 steps in that upconv. We'll now define the forward pass. So we'll say y equals self.up x. So first we do the upsample, and then we do the self.conv y. You'll notice I do this pattern a lot where I sort of make things y and then repeatedly apply things to y as we go through. There's many ways to do this. Sometimes you need the intermediate steps, as we'll see in the actual bigger unit. But just a habit that I've picked up of using y a whole bunch. All right, so that gives us our upconv. And now what we've got to do in our main unit module. Apparently my screen is frozen. That's no good. So, conv block, upconv. Let me just check what's going on there. If I am indeed frozen. Ooh, it is. How odd. me see. Please stand by for technical difficulties. All right, you can very quickly see my other screen. Woohoo! And back to this one. And did that make a difference? Can we scroll again? All right, that appears to be working. Let me know, guys, if that is not working anymore. How do we... Are we back? Can you see my highlighting? Let's have a little look-see. Let me know in the chat if we can see where I just highlighted. Hopefully we'll be back on track there. OBS seems to tell me it's moving again, but you never know. All good. All right, good to hear. All right, let's get stuck back into it. The screen capture on this, I'm running this on my laptop, is a little slow with all these applications running. All right, so now that we've built this upconv and this conv block, there's not really any major modules that we need to build on top of this. So what we're going to do now is piece them all together in the actual unit model itself. And we'll do this sort of following, we'll reference each of these sections as we go through, and you'll see how this all comes together. So this one I'm going to copy paste because it is a whole bunch of basically the same little bits and pieces, which I will then just talk you through, and it saves me having to type all of this again. So what we do here is for each of these labeled sections, we prepare a conv block that starts out at channels, goes to 64. We do a max pool. We do that again. We do that again. We got MP3 here, hence the emojis, and C4. I thought it was funny at the time. So we go down all the way to D. So you'll see there's one here for A, B, C, and D, which is why we made these blocks in the first place. So we can say conv block, conv block, conv block, conv block, and then we do these down samples. And then on the way up, we've got conv block up, blah, 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 all the way to the end, which you can see coming through here. So we got another conv block, and we start to go through here. Now, one thing you'll notice is that we do some funny stuff with the sizing of parameters. On the way down, it's pretty simple. Doubles every time. On the way up, it goes from 512 to 1024 and then back down to 512. Then back up to 1024, then down to 256, back up to 512, down to 128. And the reason for that is we have these concatenation steps here. So at each of these levels on the way back up, we grab all the features from earlier, from this last output of the conv block, and we concatenate them to the features from this upconv. And that temporarily doubles the feature size, and then the convs start to bring them back down. And you'll see that when we actually build the forward pass. But that's why some of these numbers are a little bit counterintuitive. Now, if you're looking at this and thinking, why didn't we just stick all of these things in a loop or something more fancy? I'm really being verbose here to help explain all this code. In practice, you would probably use something like list generation and do all of this. But again, here it's easier if I'm pretty explicit, and it'll tie in nicely to the forward pass. Before we get into the forward pass, the only other thing to mention is this very final convolution, which is our 1x1 convolution that starts at 64, the output here, and does a 1x1 convolution that ends up at classes. Again, with the padding is the same. Now, in practice, if you were doing this for work or trying to do a number of experiments, maybe a bit of hyperparameter optimization, you might abstract some of these sizes into parameters or constants somewhere in your file. Again, because we're being true to the paper, I haven't done that here, but in future versions we might pull some of that out to be more interesting and more flexible, I should say. All right, so now let's actually implement these. And I'll do the first couple, and then again, I've written a lot of this already, so I'll bring it in so that you don't have to watch me type the same thing 9 times. So we're implementing stage A here, which is this first conv block, this first down, and also saving the features that come out of the conv block to then later be concatenated onto the features once we get right over the other side of this U shape. Hence the name UNet, if that wasn't already obvious. So we say y equals self.c1, which is what we defined up here, conv block 1 of x. Then we want to save the variables. Skip1 equals y. We just store that temporarily. And then y equals self dot maxpool1 with y as the argument. So the reason we didn't put the maxpool in the conv block is because we need that intermediate step. In different setups, you might have lumped that in there because you could probably rightly say that each one of these has a downward step as well, a maxpool, but it also lets us use this conv block on the way back up, which is handy. So if you can imagine, we do that a bunch of times on the way down. So I'll put the rest of those in there. And that gets us A, B, C, and D. So what we've got now is right at the bottom, we've got Y, which is about to feed into E. So we're kind of sitting here in terms of the features. And we've stored this set of features, this set of features, this set of features, and this set of features, one for each gray line in the variables skip1, skip2, skip3, skip4. So now I'll write the first one of these upcoms, and then because it's repeated again, we'll do a little bit of, what do they call it, cinema magic, and just put it in. So y equals self.convolution 5 of y. So we're right in the bottom here, I should say. So we've got one more conv block, then we need to do our upconv, and then we need to start to work out how to do these concatenations, and then that feeds into that same process over and over again. So we do C5, then we do our upconv, which is self.up1 in this case. And then we want to do the concatenation. So for this, we'll use torch.cat. There's also torch.concat. They're just aliases for the same function. And then we concatenate skip4, which was the sort of last one here we did before going up, to the output of this up convolution here. And because we're using PyTorch and the batches go batch channels width height or XY, I think rows, columns, we need to concatenate along dimension 1. So we want to concatenate along the channels dimension. If you're implementing this in TensorFlow, TensorFlow tends to be channels last. So here you would be dimension 3. But because we're doing channels first here. Sometimes I think as well if you're using the CPU, it puts channels last. But anyway, the main point here is that it should be concatenating along the channels dimension. So at this point, at line 117 here, what we've done is we've taken it through this E, we've done the upconv, which will give us 512 features, and we're going to concatenate to the start. It doesn't really matter what order you concatenate them. Another 512 features, giving us 1,024 features here, or channels, to then feed into this next block. And then we do that several times. So let me just pop the rest of these in, and then I will turn to chat. And lots of blocks of variables to keep track of. Any tips for not accidentally calling the wrong variable? Yeah, so in practice, you might do this in a more structured way with, say, a loop or something else, so there's less independently named variables to keep track of. When I did this the first time, I definitely did mix up a skip 3 and a skip 4 somewhere. You have to then look at the PyTorch error messages to work out where you've messed it up, and then go back and fix it. Again, in production, depending on the situation, I probably wouldn't do this with so many individual steps like this. Anytime there is very similar code repeated like this, it says use a loop. But for the purposes of going through this here with everybody watching, and also in the early stages when you might want to experiment and tweak things and do some odd stuff, it can sometimes help to have it a little bit more spread out. For example, if you wanted to... what would be a good... Oh, it doesn't matter. Anyway, I think you get the point. So anyway, we continue to do this concatenation, convolution, upsample all the way to here, and then we do our final convolution, which gets us the channels as the output. So we'll start in our case with images of 128 by 128. Each one of these max pools will halve the size. So here we're going to have 64 by 64. Here we're going to have 32 by 32. Here we're going to have 16 by 16. Here we're going to have 8 by 8. And then we start going up again. So here, after the up, we're going to go back to 16 by 16, which is why we concatenate that with skip 4, which is before this downsampling, before this max pooling, and is that same size, 16 by 16. One thing that I often get tripped up on with these units is concatenating the wrong skips to the wrong Ys on the way up. And it's a big reason why I just didn't do this cropping business. Because in the original paper, you can see here that this image is 568 by 568. But when you go down all these ways and then come back up, the image you expect here is 392 by 392. So to concatenate these, it needs to take a center crop of this original feature map and then concatenate that center crop. Now, it's not technically difficult to achieve, but it is an opportunity for typos and mistakes, and it makes the code look a lot more finicky than I think it needs to at this stage. So I left that out here, but if you're looking for ways that it's slightly different to the original paper. Any value to an additional step, e.g. a 4 by 4. Sometimes you can do that. You can go all the way down depending on the size of your image. One of the interesting things about the UNet architecture is that because these are all convolution layers going down and then coming back up, they are somewhat invariant to the size of the original image. There's no reason you can't use the same convolution kernel on an image that is, twice this size or 2/3 of this size, assuming that the powers of 2 sort of come up and come down, which can be pretty handy. It requires a little bit of extra configuration in PyTorch or TensorFlow to get it to work on abstract image sizes. But if you were, for example, to flatten these and use some dense layers and things like that, that's where you start to run into some trouble, given that it'll expect a certain amount of variables, and if you change the image size, it won't happen. But some modern implementations are somewhat size invariant. But that being said, if you have a massive image, let's say you're working with a digital pathology image. So that's a tissue sample that's been put on a microscope and imaged under a microscope. You're going to have thousands, if not tens of thousands of pixels in both dimensions. You cannot reasonably build a unit that big on modern hardware, even with the massive banks of GPUs that people have access to. So what you'll do there is you'll break that image into overlapping patches, feed them through a network like this, and then reassemble those patches into an overall segmentation map. That's how a lot of these digital pathology startups would work. The other thing you can do is you can design these at that sort of low resolution, and then you can design them for the same image scaled down by, say, a factor of 2 or a factor of 10. And so you can get a very coarse segmentation map by feeding in a sort of thumbnail version of that image. Take my head up here, you build a segmentation on that, which will get a little bit of detail, but there's less pixels to work with. And then you'll feed it into this one, and it'll give you the rough outline, but then you can refine that with a more advanced UNet at the high resolution. But anyway, we've come to the important moment of actually seeing if this trains. So let's come down here. So what I've got here is I have a little bit of a training loop already defined. It's the kind of one you'd find in a lot of the PyTorch tutorials. Try to keep it pretty simple here. I've put the hyperparameters into this dictionary, which might at first seem like an odd thing to do. The reason I do it is because I often use weights and biases to track experiments and things. And you can feed a dictionary of hyperparameters into your weights and biases config, which will then map these against your training results. And you can say, okay, was there a learning size or some other parameter that led to better results? So it can be handy for that purpose. But if you were just doing this yourself and weren't planning to do that, you could easily make these variables. The next thing that we're doing is we're checking if Cuda is available. So if you're running this at home, once the code is up, if you have a GPU and you have PyTorch with the GPU installed, this will run on the GPU. Otherwise, it'll use your CPU. This will still likely train on your CPU, but it will be slow, much slower than training on the GPU. So what do we do next? We instantiate the model with our 3-channel input and our 2-channel output, the 2 channels being background and pet, and then we push it to whichever device is available, ideally Cuda. For the optimization here, we're using a cross-entropy loss, so pretty standard in classification problems, and here we're classifying each pixel as one of 2 classes, so this works well. We're using stochastic gradient descent on all the model parameters with our initial learning rate. Recently you might pick Atom as a better default, and you might do something like learning rate scheduling or cosine learning rate decay, which we'll do in future videos, but again, harking back to the old school, we'll just use SGD. I think in their original paper they had a momentum term which was quite high because they were doing patched segmentation on some pathology images, I think. But this is enough to show that this will train, which is the main thing that we want to achieve here. So the next thing we do is we take our data set, which is about 3,500 images, so it's not huge. It really is not a big data set. And we split it 80-20. We just calculate the length of 80% of the data set. We then use the random split function. Because we have a fixed seed, you should get the same random split as me. And we split that into training and validation. We make a data loader for each with the batch size. And what this will do is it'll just take one batch at a time. And it creates a generator, a Python generator, which is quite handy. And then we have our train loop. So normally you'd have a test loop and other bits and pieces here, and we might put one of those together after this. But in prep for today, I just wrote this train loop, and we'll do some experiments on what the actual outputs look like. So we've got, in our train loop, it takes one of the 2 data loaders. In this case, it'll always be the train one. Takes our model, the loss function, and the optimizer, and it runs through in batches. And it grabs the input images and the input labels, runs the images through the model. We shift the images to the device, in this case the GPU, and get our predictions. So predictions here will be, let's say our batch size we set to 64. This will be 64 images of 128 by 128 by 2. Actually, the 2 will be at the front. But it'll be the probability, or it's actually the unscaled probability, the logits, of each of the 2 classes, the background and the foreground. If you wanted to get the probabilities, you'd then put a softmax on the output prediction, but we're the loss function's happy to take logits. It's actually more computationally efficient to take the logits. But anyway, we then calculate the loss on our given loss function, which again is cross entropy here, compared to y, which is the true segmentation maps. Now, cross entropy can take one of two different formats. You can have one channel per class with the probabilities, or like a one-hot encoding, or potentially not one-hot encoding if you have sort of blurred images, say overlapping. Or you can take a 128 by 128 image of longs, where each pixel contains the index of the class that that pixel belongs to, which if any pixel only has one class, that can often be a little bit easier. So then we zero the gradients, we do the backwards step, backwards propagation of the loss that we just calculated, and we do the step. And then every second batch, just so we get a lot of printing here, we grab the latest loss, we calculate how many images we've fed through this image, and we print it out. And you can see here, normally we'd do this for 5 epochs, but I just did a test here with a single epoch. So what we'll do is we'll save this and we'll run it all from the beginning and hope we didn't make any copy-paste errors. All right, where are we? All right, good stuff. So you can see here it's using Cuda. If I temporarily pull this little metrics panel up, we can have a look at the GPU usage. Oh, wasn't happy with that. Oh, it's just a warning. Oh, yeah, okay. That's just telling us about the padding, that it can sometimes create some extra data that we might not need. But you can see here it's jumped onto the GPU, starting to draw power. These graphs don't update all that often. And it's moving through the batches. Now, as I said, there's not a huge amount of images in this data set. I picked it because it was small and picked it because it would be quick. But you can see here, it is starting to learn. So the loss, the cross-entropy loss here, which is the average cross-entropy loss, is slowly going down as we continue to go through, which is a good sign. You can see we've allocated a bit of memory on the GPU. It's only about 11%. And then, so yeah, we could definitely do a much bigger batch size. Can you plot the segmented outputs on each step of training if possible? Absolutely. That is actually what I was going to do next. So we'll start to make some raw code changes, and you can expect a lot more syntax errors from this point onwards because I have not prepped, but you're seeing this fresh. So what we will do while that's happening, we will add another, oops, didn't want to add that above, I wanted to add that below. I'm just going to get rid of that one. And set code below. My screen's really zoomed, so I can't see that whole menu. Tom says, why was a loss already defined at 0? Yeah, so at this very first step, it has technically done one step of training, but even if you printed loss, actually no, it hasn't by that point. The reason is when you start this training, it initializes all the weights to random values. And those random values, while they're not going to be good, they are going to produce some sort of output. And that output in this case got this loss function. There is a whole branch of machine learning which is how to pick the best initialization for weights. Obviously, you can't pick initialization that well that you don't need to train, but there are certain optimizations you can make that start you at a much more favorable position. Now, what we'll do quickly in range is start to do this train loop multiple times. So we'll continue it training, and we'll also make a little adjustment here to see if we can print out that image somehow. So what we'll need to do is we've got our prediction So we'll grab maybe the first image out of the batch. It should be a batch of 64 equals prediction 0. And now, I don't know what shape that's going to be. It's probably going to be channels by 128 by 128. So what we could do, because we only care about the pet, we probably want the image equals x0, because we'll probably want the image as well, which will be 3 channels. Let me just quickly look up how to, in PyTorch, move the channels around, which I've done a bunch of times, but I can never remember the syntax for it. Oh, code froze again, did it? Oh no. Let's do this again. Switch displays. You can see OBS forever. I will find a better way to do this. All right, that seems to be back at least. Firefox. All right, so what we want to do is here we've got 3 by 128 by 128, but pyplot or matplotlib wants 128 by 128 by 3 if you want to display it as an image. So the function for doing that is permute, I believe. So we want to go permute, and we want to have 1 and then 2 and then 0. So that gives a new order for the dimensions. So it takes 1 and then 2 and then 0, which should hopefully, if all things go to plan, image. And then what we'll do is we will plot.imshow prediction with an alpha of 0.5, plot.colorbar, and plot.show. So if that worked, which I'm not 100% confident it did, that should plot the... did I just start the model again? I don't know, it doesn't matter. Should plot them on top of each other. So we'll try in our new code loop. Hopefully the thing is shown again. No, didn't like that. And there's a cat, so I got that bit right. Cannot convert. Oh, of course. So you need to get stuff off the GPU back to the CPU. In order to use it in something like matplotlib, which can be only element. What did I do? Maybe that'll work. It's always fiddly getting this stuff back out. Didn't like that. Prediction. Let me just check what shape this is. Print it. It will crash. That's fine. I just want to get some visuals. So it's 2 by 128 by 128. That's fine. Oh, it tells me what to do. But the other thing we want to do is actually just take the first channel, which is the cat class, or the pet class. I think there's dogs and cats in this data set. Oh, it doesn't like that. Oh, good. You also need to do this. There's probably a cleaner way to do this, but that'll work for now. All right, so it is now printing on the first image in the batch, the image, and then overlaid with the, it's the logits, I guess. That's not going to be that helpful. So we need to do a softmax. But anyway, it's printing and overlaying. Let's see if it gets towards anything useful. But we will do a softmax so that the numbers are actually meaningful. So right now, this is just the logits. So it's going to do e to the power of this number to get, and then normalize it to get the probabilities, which is not super helpful. One thing you will notice here, just before we go back and fix that, is you can see this yellow banding around the edge and some of these sort of artifacts around the edge of the image, especially in the early stages. That's what comes in from the padding often, is that when it pads it, it fills it with zeros. And images that are usually light around the edges and then switch to zeros, you'll get sort of artifacting around the edges, which can be a reason to not do the padding. But it eventually learns to ignore that. But before we do this, let's just... it's not doing anything particularly interesting. Okay, doesn't like doing that many prints anyway. So we'll make it print a little bit less. We'll restart the kernel. We'll maybe do every 20 instead of every 10, especially if we're doing 5 epochs. And then I need to do softmax. Let me just look up the syntax there so I make sure I get that right. So we want to do nn.functional.softmax on that, and the dimension is going to be 0. So normally it'll be dimension 1, which is the channels dimension, but because we've already taken the first element here, that's going to be the channels. So this will be size 2 by 128 by 128 as opposed to 64 by 128 by 128. And for the minute, we'll just do 1 epoch just to make it a little bit quicker. So we're just running all that code again. We did restart the kernel. But what we've added here, softmax, if and when it works, will now normalize the values to be probabilities, values between 0 and 1. And you can see here they all start sort of roughly around 50%, which you'd kind of expect. It doesn't know if it's a cat or a dog at the early stages. But over time, as this continues to train, we should hopefully see this get a little bit more dispersed and start to predict some things as background and some things as foreground. But we'll let this do a little bit of training. What I might look at actually is how much GPU RAM memory are we using, because if we can get a bigger batch size, so we're using about 50%, we can probably double that batch size. It'll train faster, and if it trains faster, then we should see progress faster, which is always a good thing. But you can see here it's not... Oh, that was 1 whole epoch already. Didn't do very much exciting stuff. So let's do 10 epochs. And the other thing we will do... Let me just work out how to do it. Is set it so that regardless of what the actual probability values are, it will... Yeah. We'll do it here. CLEM 0, 1.0. So what this will do is it'll make sure that the range here from sort of purple to yellow is always the range from 0 to 1. Because that means between images, it'll get a consistent sort of visual. Whereas right now, it, as you can see, it just sort of rescales based on the data that's available. So you can see now it's sort of 0 to 1, and it's all sort of this light blue color because it doesn't really know what to think yet. And we'll let that train and get a little bit further along. Now, while we watch this train, I'd like to talk about, and we'll come back down and have a look at some of these outputs. some of the optimizations that I think, even if you were sticking to the original UNet architecture, I would definitely make, just given what we've learned about machine learning in the last however long it's been since this paper came out. The big one of those being batch normalization. So batch normalization is a way to correct for the fact that between each of the layers in your neural network, you can start to get features that have sort of means and variances that start to drift off in a certain direction. And that can sort of bias your overall network in a way that makes it a little bit harder to learn. Now, typically, batch normalization won't make something that would never learn, but it can get you to a point of useful output a little bit faster. So we'll add that in as an addition to this. But we will let this continue training, and we'll see where it gets to. You should see the same few images a few times here because it is not shuffling the batch between epochs, which is probably best practice in the scheme of things, but for the purposes of this video is not that critical. All right. So it is learning very slowly. I did pick that learning rate arbitrarily, and we may need a ton more steps than we can do here before we actually would expect to see something good. What I might do, it's kind of hard to see where these probabilities actually are on here, if they're changing or anything like that. It does very much feel like it's just hanging out at the 50% mark, which it probably is, to be honest. Like the loss has gone down slightly from maybe 0.67, but it hasn't gone down a whole ton. This is by no means an optimized training setup. The high parameters haven't been tuned. So there's a whole bunch more stuff we might want to do. All right. I think we can pretty safely say that while this is learning, this stream will very quickly become pretty boring if we just sit here and watch and wait for this to train to a reasonable amount. But we got to about 0.659. So let's remember that, because what we're going to do now, we'll go back to the start. So it started at 0.673, so it learnt a bit of stuff. Not a huge amount, though. We're going to add batch normalization in and see, you know what I really should do, just for our own sanity next time, is print the batch, some sort of thing to say when a batch starts and a batch ends, so I can work out what batch we're up to. Because now we just got to count cats. So 1, 2, 3, 4, 5, 6, 7, 8 cats. So this is batch 8. I'm not seeing a huge amount of difference. It might be too opaque to actually tell if there's some stuff going on here. So what I might do is additionally turn up the alpha so that it's a little bit less transparent, and if we do see any drastic changes in color, we'd see that pretty easily. Color. Ooh, I feel like a boy in high school again with my voice cracking like that. All right, we'll make this 0.75. We'll restart the kernel, and we're going to go up and add batch normalization. As I said before, I am going to download this Jupyter notebook. I'll put it up on GitHub, so you'll have access to this, and all future streams I will make available as well. You know what? Okay. Well, anyone with this link can view this notebook. So if you do want to have a look at it literally right now as we go, there's the notebook. But yeah, I'll put it up on GitHub. Hopefully that doesn't give you edit permissions. Otherwise, this is going to become multiplayer machine learning, which is not necessarily a good idea. So batch norm 2D, and all it takes is num features equals in this case f out, because the number of features at this point is f out, and we'll put that in between each of these two ReLUs here. Now, what we won't do is put one here, because this is kind of a special convolution just for this upsampling step. But yeah, you might sometimes decide whether you want to put one in other places as well. But what batch normalization does, I should say, is that as you feed it in, your model can sort of start to drift. Little changes in one direction can push all the weights, really high or really low. And if your real-world data, let's say your validation set or your test set, has different parameters, let's say different lighting conditions or different camera, different MRI scanner, the sort of features can then wildly shift to a different direction, and that can really knock your model out of whack, and it takes a little while to learn that. Batch normalization takes all of the features at each of these points and recenters them around 0. So what it does is it subtracts the mean of the features, feature by feature, and divides by the variance. And then it learns a couple of parameters to then scale that to an appropriate scale for the rest of your model. But let's run this and have a look if we get any slightly different results from this. So we will come back down to our thing. Okay, you can see now it's a lot less. Yeah, I mean, you can already see before it was very much centered in the middle. Even just adding batch norm here, I mean, it's on the very first step, so it really means nothing. But you can see that it starts to really change the output. And this dropped opacity here is giving us a little bit of a better understanding of what the model's doing. Got a little pop there. So what you'll notice actually, just to talk about some features of machine learning and convolutional networks in general, is that the very early stages of training any of these networks, you tend to get features like edges be highlighted as areas of significance. In the old school machine learning days, or image processing days, I should say, you would build hand-built edge detectors and use that to do your image detection. We're really learning that from scratch. Vivek says, shouldn't the images generated on the first epoch be garbage? Yeah, you would think that they were garbage. I think it's mostly garbage. It's what it's saying here is that like this bit of the cat is 100% cat and this bit is 0% cat. And I think that comes from just that random initialization giving you these sort of weird pseudo edge detectors in your original model. So you'll see a lot of variance in areas where the texture changes a lot, and then not a lot of variance in the areas where it stays the same. So if you had this cat, say, on a background, I guess this is a better example, this dog. It's only done, it's actually done quite a few here, but you can see that anywhere that there's high texture in these early stages, you tend to get a lot of variability in the predictions. And it won't be until later that we start to see some more consistency around these. So what batch? Oh, that should be epoch, not batch. So we're making some progress in terms of our training. You can see here that even just adding that batch norm has allowed us to, at a much sooner batch, get to a much lower loss. That other model, if you kept training it, it would have got there eventually. But batch norm is definitely just a sensible default in modern convolutional networks and gets you to a nicer solution much, much faster. You can see that as we've gone on, the areas around the animals in the pictures are starting to become a little bit more yellow, a little bit less purple. There's certainly still mistakes here, but you can see as we go, the cat in this case, and funnily enough, its shadow is starting to become more well recognized as a pet. Now, I should say, these are images from the training set. So they are going to perform better than the images from the test set. And we can run the test set through after this and see how well it performs on some of those. If we deem that this is getting to a stage of actually good convolution. But it's certainly learning. And that's the main thing. That's the main thing we wanted to get to here. Indeed. So, let's... so if we have a look here, yeah, you can see a lot of yellow around the cat here. There's still some problems with the stripes. The background's pretty... I'd say it's getting darker compared to the early stages where it was sort of... Let's go right back to the beginning. You can see here it was sort of all 50% pretty much. It was all in this sort of I don't know area. And that's what you get... around that. This happens when the unit encoder is pre-trained, right? Yeah, it definitely can. If you trained this on, some other data set of real-world images, you often get a lot of good sort of edge detection and feature detection that you can then use in a new problem. If we took this unit and let's say we got, rather than the 3,000 images here, let's say we got 300,000 images of cats and dogs and then trained it on something completely different, let's say images coming into a self-driving car or medical images, the pre-trained weights, I should say, wouldn't be super helpful, but they might perform better than a random initialization. It's hard to say. All right, learning. So we can definitely see here it is starting to improve, which is really nice to see. This dog here in particular, it's getting a nice sort of bubble around the dog, a lot less of the sky, and in general the background is getting a bit darker. This one's taken a little bit longer to get there, and we can't see any more. Oh, no, we can see more. That's good. It sometimes stops showing you outputs so you don't, use up all your RAM or some nonsense, but it's good we can show them. So you can see here the loss much, much lower than it was before, which is good, and the outputs are certainly more helpful. Now, I wonder if that was only ever going to show me that one more, or if it is going to just keep showing me them as they come. I feel like it really slowed down. But we'll see. Is it still running? Yeah, it's still going. So we'll let this train all the way through, and then we can do a test on some of the final images here. Do you have any insight what it might be learning on exactly? So I think, in this case, what it tends, it's exactly is a hard word on this, but what it, all of these models are pattern recognition models, and going through this multiple times, it'll start to learn, that there's certain patterns that appear in, say, a cat's fur or a dog's face in terms of the placement of its eyes and its nose that don't appear in what we consider to be the background. And as it learns to, to correlate that more and more and more, it learns to say, okay, this is a dog, this is a cat, and so on. So I think it cut off our training, so we'll just run one more little cheeky epoch down here just to get the final sort of cat, dog, and other dog images. And we'll compare them to some of the originals. So that was the original cat at literally step 0, so a practically useless machine learning model. A lot of the background is in that 50% zone, doesn't know what it is, and you get a little bit of texture around here. And after, 10, 11 epochs here, we are starting to see a lot more around the cat. Now, there's definitely bits that it's still getting wrong, like this area here and some other bits and pieces, but it's getting better. And 10 epochs is not, you can still see even between this set of steps and this one, the loss is going down quite a bit. So if I was training this model for real-world use, I would keep it going for a bunch more epochs, really until the loss starts to flatten out. The other thing that is common that we didn't do here is to have a test loop that runs after every train loop and validates the model on data that it hasn't seen before in training. So we did it here. We split it into the validation data loader. I just haven't written that test loop function. But that gives us a sort of independent assessment of how well it's doing on sort of newish data. And then right at the end, we would test it on our test set, which is, data that it's absolutely never seen before. Cool. So that is our dog, cat, pets. I guess those are the only two things it considers to be pets. UNet, what are we doing for time now? So we got about 10 minutes until time. I think if there's anything interesting we can do, because otherwise I am going to have to disappear. But I mean, hopefully, to anyone watching this live and anyone that watches this in the future, I hope this was helpful. As I say, what we'll do is we'll iterate on this UNet that we've built here tonight and start to add some more advanced features. So, things like switching out these conv blocks for more advanced ResNet blocks. And some, eventually I'd love to get to, the very modern sort of transformer / attention blocks in these conv blocks. Because if you have a look at, say, Stable Diffusion, which everybody is very hyped about at the moment, it has a UNet right there in its architecture that takes encoded data from the text embedding and then turns that into an image. And it uses a UNet which has a transformer block in each one of these little conv blocks. So what I'm hoping is, after a few streams, we'll go from this very basic UNet to something that is, pretty much state-of-the-art. I'll set up a few more things in the background to sort of tweak the hyperparameters and work out how many steps we need to train this for and so on. But look, I do hope that was useful. Thanks for everybody that watched live. Thanks for everyone that subscribed to the channel. And how about we call it there? Until next time, hope you all enjoy it and keep learning. See you next time. Now there's that awkward pause where I have to stop the stream. Bye, team.